Let's get started. Make sure everything's set up nicely and working to an extent. Pretty sure we're live, but yeah, there we go. No. I mean, I think we're live, but I don't see the video up yet. I'm just going to make sure I think everything's up and running. I'm just, I guess, making sure. There we go, yeah. So we have, okay. Hey everyone, how you doing? Not think anyone's here, but there isn't anyone here yet. Today we're gonna go over the Flash attention paper. On our Discord, we're gonna do a paper review on Sunday, I'm pretty sure. Yeah, Sunday. But I just wanted to read through it. I mean, yeah, so I want to get ready for that paper review a little more, so I'm gonna read through it. Maybe try and solve. Pretty sure we have a flash attention forward pass. Try and solve this question as well. But before we solve, we're gonna just go into the actual paper. Okay, let me zoom in. Make sure everyone can see. Need to keep an eye. Okay, Transformers are slow. Transformers are slow, memory hungry. No, it's not working. Can I not highlight for some reason? I really enjoy highlighting. Let's see. I'm also watching my son, so if I randomly leave, it's probably where I went to. Velocity and self-attention are quadratic sequence length. Approximate attention methods have attempted to address the problem by training off-model quality. Okay, so sounds like, I guess, they're saying the traditional, well, let's first, what is attention? Quickly, we have query, we have key, query, and value, yeah. And we take, pretty sure it's this, transpose of key, too small, transpose of this, so we all know what attention is, but I think it's over the dimension, d of k, divided by d of, I'll look this up to make sure, I just want to see if I actually remember it by myself. So let's first try and understand what attention is quickly. And then we'll get into all of this gets bigger version of all these things. Okay, this, this, and pretty sure we do soft max over this, and we multiply that times v, and this is attention. Let me make sure that it's actually attention. Let's go to the actual paper and make sure it's, because this is what they were improving on. And so it's a square root of dk times v. Oh, I was so close. Was I so close? Oh wow, yeah, just missed the square root on the bottom. SQ t. So just missed this. But other than that, anyways, I mean, I don't think this is just a normalization factor, I'm pretty sure. Okay, so what did I do? No. So we have softmax of, you know, this. I mean, so this is how we compute attention. If anyone has any questions about intention, let me know and we could dive deeper into this, but I'm going to assume we understand attention. Okay, so that's attention. So first, I guess, they're saying, okay, they're saying memory complexity and time complexity are quadratic. So I guess first let's try and understand that piece, and let's see what's wrong with it. I mean, maybe, let's see, chat. What is the complexity? Not thinking, it's too early right now. What is the complexity of tension? Length of the sequence n. So theoretically, the longer the length of the sequence. Let's see. To compute. Okay, let me actually read this a little more rather than just gloss over it. I feel like sometimes I'll just look at something and be like, yeah, I understand it. I mean, it's sort of the idea behind DeepML is just like you can't just be like, yeah, I read it, I know it. You sort of have to prove that you really understand it. What is memory complexity? Okay, compute scores of QKT. Okay, that's it. So for every, so if I have a word, is this just not working? Okay, or not. Okay, control box. What? No. Delete this. There we go. If I have a word, I have a cat. Every word gets encoded. Assume this arrow means encoded into, you know, a query key and value. There's actually 3 values, and for every query, so I have I gets, basically we're looking at every other word. Let's assume we have. Yeah, assume I. So we have I, and then I is do q of I, q of 1. And that would be the query of the first one, and this would go, basically we would do the dot product for q F1 compared to K1, K2, K3, dot dot dot. So for all the words in this thing, we would, I mean, I guess it's a vector multiplication, so I would imagine it wouldn't be so complex. Let's see what they say. Yeah, so Q is a vector, so we have an n by d dimensional query, and we have a d by n. So n is the number of words, I'm assuming, and d is the dimension of the encoding. So n equals num words, number of words, d equals encoding dimension. So encoding dimension is basically like all of these, each one of these goes into a token, and then from token it goes into an encoder, and the encoder, different encoders have different outputs, but I guess basically you're encoding this word into a set of numbers. So you could have, you could have 100 dimensional encoding. That means it's just a store of value, just basically saying this vector is equivalent to I, and then you have another vector that goes through encoding, and that would be equivalent to have. I mean, for attention, we actually have 3 different vectors. That's the query, key, and value. But in simple encoding, it's usually just one number, but theoretically, we're going to get 3. And that's the D right here. So in this case, it would be 100. And back to here. So query is the number of words. So 1, 2, 3, 4. So theoretically, we would have, trying to think how to put this nicely. We would have this, this, and this would be give me an example. Sequence length is 4. Dimensions is 3. Yeah. Probably should have. Okay. Fine. Let's follow their example. It's probably hard to show 100, but 3 is easy. So we would do a 4 by 3 matrix. So there'd be, this would be 4. This would be 3. And inside this one is called Q. So we have Q. Like that. Let's copy this. So that's Q. Then we have K, I'm pretty sure. And K is the K transpose. K transpose is the dimension. And okay, yeah, it's the same thing, it's just reversed. So instead of 3 by 4, it would be 4. It would be 4 by 3. And this would be the key. Would be the key transpose. So yeah, if we dot these together, we would get a 4 by 4. because this is 4 by 3 and this is 3 by 4, and you would get a 4 by 4 matrix if you dot product these together. Yes, true. Output is n by n. That's true. Cost of doing this is n squared times the dimension. I mean, wouldn't the dimension eventually fall off and just be n squared in terms of really big n? So both of these seem to me to be n squared. I mean, I guess I don't. Is the dot product that expensive? I'm saying a dot product is n squared. I don't know why I thought it was a lot faster. So this is O of n squared. Let's see. So we're saying we have this, we have that. I guess you're doing 16. Okay. So you're doing 16 dot products because you're doing. Let's make. I mean, you're doing this transpose. So this is 3. Yeah. I don't like how they didn't give me the matrix already transposed, but taking this, multiplying like that, taking this, multiplying like that, and then, okay, fine. So you're doing 16 dot products, as in like each vector gets multiplied, and doing that 16 times. And these are 4 by 4, and that's n, so it's n squared. Fine. Each dot is length 3. Okay, so because the encoding was a 3 by, I mean, we're encoding things into 3s, so theoretically, this is the first one. Just take this. Theoretically, the first one, so this right here is the encoding of the first word, the second one is the encoding of the second word, and so on. Same thing with K, and same thing with V. So we're basically dot product, I mean, K should be transposed, but basically K is transposed, and you take this, multiply times this, or, yeah. And, okay, so it's basically going to be 16 computations, I guess, and that's how we're counting it. Yeah, that makes sense, fine. Depth of 3. Okay. So this makes sense why it's n squared. Let's see, so we have n squared. So I guess this process, at least on top, is n squared, and then they're saying the softmax is also n squared. At least up here. Variance slash attention, so time complexity seems like it's going to be the same, but it looks like we're going to be tackling memory. So let's actually look into why is the memory complexity n squared? Because I guess we're going to have the same time complexity, which I guess... Let's see, softmax, each row, softmax is n by n. Multiplying with values of softmax. Okay, that's total cost, fine. Let's explain. Sneeze. Okay. So if you have 512 words, so you'd have, damn. Uh, so as the number of words increases, so it's squared the number of values that you will have, or I have to keep track of. Let me just make sure I understand this. Because I guess we will have to keep this value. I mean, we'll have to compute Q of KT for every single, we'll have to compute this value for every single word against every single word. So for I, we have to compute it against have, I, cat. Then for have, we have to do it the same thing, and A, the same thing. But for I, we computed this value for everything, and you have to keep those, you have to keep this value. Okay. And I guess at the most we're going to keep is these matrices, which are, as we said before, if it's a 3 by, I mean, it's going to be a 4 by 4. Okay. Anyone have any questions? Hey. Okay, so what we learned so far is attention is great, but it seems like computationally and memory-wise there's an issue, and the objective of the flash attention paper is to try and deal with the memory concerns. But let's read through it a little more. Okay, approximate attention methods. Okay, so it seems like currently people have, or at least in this time frame, people did approximations for attentions, but they're giving up model quality for compute complexity. Yeah. Between GPU memory. Okay. I don't know. Yeah, my knowledge on GPUs is not the best, but I guess that's why we're reading this and trying to learn more about it. Oh, hey, what's up? Any questions or any thoughts? We got one person in the chat. Okay. Argue that the missing principle is making the attention algorithm I/O aware, accounting for the reads and the writes between levels of GPU memory. Process proposed flash attention. Yeah, I probably should multi-stream. Is there a good way of doing that? And also, I feel like I stream more to just help me study, because I feel like it's a lot less distracting when I know one or two people are watching, if even. Yeah, it just makes me a little more efficient and make sure I understand things, because I can't just glaze over it as easily. But I probably should. Might as well just stream on Twitch as well. But I was wondering, is there a platform that I could just do it easily? Because yeah. Let me know if you know of a platform that I could use. Like I'm saying, that will multi-stream. I probably could just search it up, but I'm lazy right now. Okay, that missing principle. is making attention algorithm I/O aware, accounting for reads and writes between levels of GPU memory. Oh, I really like TinyGrad. I mean, we have on DeepML. I always feel bad about this. I feel like we have a few TinyGrad questions. One, I don't even think it's more than five. I really want to work on it. Yeah, okay, we got a few. um, I think what they're doing is really cool. I mean, I really like George Hotz's. Yeah, we only have two. I really like George Hotz's streams. Those are really interesting. Uh, I think the work he's doing is very valuable because I do think right now, I guess, my understanding of his idea behind TinyGrad and TinyCorp is NVIDIA basically gets a markup on all their GPUs and all their flops because they have CUDA and it integrates nicely with everything and it's easy to actually run these things. But the value of the compute isn't actually worth as much as, I mean, there's a big markup because there's no one else, there's no competition. So I think TinyCorps or TinyGrad is like, hey, we're going to make this library that people could integrate well into AMD GPUs and any other kind of GPUs, uh, just to make the market a little more competitive. But I do like, I mean, yeah, I would wish I haven't contributed. Let's see. It's all based on the bitter problem. Is that like the bitter, uh, the Richard Sutton paper or article? The bitter lesson? But I think, I mean, I'm pretty sure, I guess, is this working? I think bitter, yeah, the bitter lesson. I think Kama's principles are on the bitter lesson, which is my understanding of the bitter lesson is like the more hand-drawn things you have, like the more, oh, I'll use George Haas's again. If I have a cone guy, and I have a different model for every single part of self-driving, that eventually that process won't win out to just a completely automated process where I just have an input, a model that reads the raw input, so reads the driving data and just makes the decisions like that. Versus if I have inputs, 10 different models, one detecting cones, one detecting stoplights, one detecting this, one detecting that. Eventually that process will break down. Let me know if I got that. Yeah. I love the example of the cone guy. um, what do you mean by it's more of a software problem than a hardware problem? I wish I just had you on chat. Rather, I mean, just could talk because there's a delay in what you're writing and what I'm saying a little. But I guess let me know what you mean by software problem rather than a hardware problem. I guess. I guess computationally it's an issue. Oh, or are you saying like I guess it's hard? I don't know. Let me know. But I do think it's an interesting thing where yeah, just like a system that will be able to take in raw input, use it, and make a decision will eventually beat out all of these hand-drawn models. Oh, cool. Um, yeah, I feel like security is a cool field to be in. I don't know much about it. And I feel like also security makes like the requirement is for you to really understand things well because if you don't, then things will break or things will fall apart a little more versus. Uh, Any other stuff actually comes from security. I guess he discussed on latent spaces about this. Is latent spaces like a podcast or Was that you talking about like the actual latent spaces? Let me know. I'm gonna continue a little bit. Yeah. But yeah, conclusion, I do really like Latent Spaces podcast. Okay, I remember I saw one of George Hotz's podcasts recently. Might have been that one. I just don't know the name of the podcast. Uh, he was basically saying how I guess it was a hardware issue rather than a software issue. I mean, that's also an interesting conversation, I guess. I don't know the difference between. I feel like there's numbers about like speed up you get from hardware versus speed up you get from software. Yeah, okay, fine. We'll get back to it. I could ramble on about this random stuff for a while. I enjoyed the getting sidetracked and random conversations. Let's see. We're recording reads writes between levels of GPU memory. So I'm saying the issue is with my understanding of this is there's an issue with how the GPU is communicating the reads and writes. Let's see if we'll read on, and I feel like I'll know if I'm right or wrong later on. Burroughs flash attention, an IO-aware exact attention algorithm that uses tiling to reduce the number of memory reads and writes between GPU high bandwidth memory. Okay, I mean, there's a few things I don't understand right here, like the use of tiling. Am I supposed to know what that means? I do not know what that means. SRAM on chip SRAM. Yeah, my knowledge of GPUs is very minimal at the moment, but that's why we read and learn. I mean, might as well. Okay, using tiling. What is tiling? Where am I? Definitely spelled that wrong. Definitely. Oh, okay. I'm happy it actually understood me from the previous context of the things I was talking about. Tiling is a memory. What's called blocking is a memory optimization technique where you break a large computation into smaller blocks, tiles, so that each tile fits in faster memory. Okay, so each block would fit into a GPU instead of slow memory VRAM. Okay. So we have an example compute. Okay, we know this is the crux of the attention, what it's actually doing. Okay, yeah, blah, blah, blah. So you split, okay, so you split them into tiles, but how would that actually help? Q tiles of shape block size, so I'm assuming this is the tile size. But, okay, so I guess this is, should I try and draw here? Let's see how this goes. Okay, drawing will be faster. So we have, but a lot uglier. Good luck, guys. So we have a bunch of, one, 2, 4, 2, whatever. We have a bunch of values. This, we'll call this Q. And then I guess my understanding of tilings right now, we break this into smaller tiles. It's a bunch of a CNN. Whatever. something like this. But let's see if it's actually correct. Compute the tension of one block at a time, like a grid. So yeah, obviously the submatrices will be probably should add another number to make my life easier. Whatever. Assume there's another number here. So we take small blocks. So this is tile 1 of, and then okay. With tiling, you load only a small tile of the Q into fast memory. Load a tile of K into fast memory. Okay. Compute the smaller block. Let's say it's 512, and you're doing 128 instead. Okay. Huh. Let me see if I actually understand this. I think I'm starting to understand it. So you're basically taking this block, throwing it to a GPU, doing the computation on the smaller block, and that will cost, well, here we also have the other one, but this will cost just the size of this, which is 2 by 3. So it'd be a 2x3, yep. And that would be Q, and then you'd have another one, which would be 3x2. And when I say another one, I mean this is Q, this is K. So you do this, and you get a 2 by 2 matrix in the end. Gotta stop holding on to shift. You'd get a 2 by 2 matrix at the end of this. You would do. I'm a little confused. Okay. A small. Okay. Have Q into fast memory. Load the tile K into fast memory. When they say okay, load only a small, when they say small tile of Q into fast memory, does that mean a small value of the Q, but the full tile of K? Load a tile of K. I think it's the same thing. Okay, yeah, it has to be. Compute the block, so we get this value for that subset. That subset, okay. I'm confused because I guess I would get, this goes to the GPU, we compute this, we get a 2 by 2 matrix, we compute softmax on that 2 by 2 matrix. What do we do with the softmax is, I guess, when we're done with this. Immediately use softmax, discard it. I'm assuming they meant discard the matrix we just made. Okay. For each tile Q, for each tile of K, load Q, load K, compute a small score, update the softmax stats, discard the score block. Okay, and you're left with the softmax stats. I don't want you Oh, that could be a good question though. Oh yeah, I mean, probably an easier version of this would just be a tiling question. Let's see. I guess maybe I should work out an actual example. So I send this to the GPU, and I get this 2x2 matrix. When they, sorry. I'm saying if you're getting a 2x2 matrix, you're doing the softmax, update softmax stats. Okay. Dive. Give me an example. Okay. Given a 4x2, 4x2, we do that, fine. It would, okay, so usually this would be a 4x4 and take up that much memory, but we're going to do block sizes of 2. Coolsies, so that should be the first two, these two, and I guess we're transposing it, so yeah, fine. Now we compute tile by tile. The full attention matrix would be tile 0. Tile 0, 1, 1, 0, 1, 1, fine. I guess 0, 0 is this. I guess it's 0 and 0, so it's this one and this one. 0, 1 is 0, 1, 1, 0 is 1, 0, 1. Okay, fine. So different tiles and different mixes and matches of these things. Cool, these. Tile 0, 0. Fine. The transpose of fine. Okay, we compute. Okay, yeah, we computed these. Okay, so we're computing all of the things. Oh. You want to share the link for the diagram of tiling? Or is it actually in the paper itself? I don't think it's in the paper. Oh. Let's see the, oh, I didn't know if I said, I see a diagram for that. Let's go. So I guess it tiles things into, so each matrix gets broken up and then each part gets sent to a GPU. Sure. Okay, so we do each computation, so we do this. I don't see where the, I guess the softmax part was really annoying me. But I guess they compute every single tile, so they compute this tile, and then they stitch it all together into, because this should be 1, 0, 1, 2, so that should be tile 1. This is tile 2. Okay, so we compute each tile. Let's compute, goes to GPU, and then we take the 2x2 results and put that into a new matrix, which is this matrix. Oh, you're not going to make me a diagram? Please. I never usually say please. I mean, I say please to people, but I usually don't say please to chat. Okay, back to... Okay, so you tiled them together. So I guess at any point it's only holding a 2x2. And then I guess at the end it's holding this, but... It's so weird how that works. You just tile things up and it's just like, more efficient. So I guess this is the same as just doing it. Yeah, okay, so this is the same as doing the full thing. And once we get that, once we get the results from there, we would do this. Okay, so I understand tiling. Does anyone have any questions about tiling? I sort of understand tiling, I think. Okay. Back to the paper. Back to the abstract of the paper. I mean, I'm taking my time with the abstract. I'm trying to understand all the small details so we fully understand this. We'll see if we'll even get to the paper today. Flash attention. Okay, so tiling to reduce numbers of reads and writes between GPUs and high path memory. Okay. Thank you. I gotta check on my kid. Sorry. I think he's starting to wake up. I'll either be back in 5 minutes or 20 minutes, but yeah, I'll be back. Sorry. And I'm back. Sorry about that. Let's see. We analyze the I/O complexity of flash attention. Okay. Probably should look up what. I don't think it's necessary. Whatever. It's making things more efficient. I don't really know what high bandwidth memory is. Like, I don't know how things work, but it's basically saying, like, send things to GPU, does computation, comes back. I'm just making that process a little faster. Extend flash attention block. Okay. Also extend flash attention to block sparse attention, yielding an approximate attention algorithm that is fast. Okay. Am I supposed to know what block sparse attention is, or are you going to explain it later in the paper? Also, why is this not highlighting? I really don't like it. Whatever. Maybe we'll dive into this quickly. I just want to finish reading the abstract, and then we'll go into understanding a little more. Okay, flash attention, trains transformers faster, 15% end-to-end wall clock time speed up. Nice. Oh my god, I haven't read the word BERT in so long because it's been like now it's all LLMs and LLM this and LLM that, and chat and Mistral or Mixtral or a bunch of things. But the word BERT, it brings me back. It's like Google's old series of language models. It wasn't really. It was very different back then. It was like more you had a different model for everything, like model for summarization, model for translation, model for this, model for that. And I feel like it all just got mushed together into LLMs. Oh, GPT-2. GPT-2 ChatGPT was just I think it was just token prediction, next word prediction, if I'm not mistaken. Flash attention. I want to read the. I never read it end to end. Maybe the GPT-1 paper. That would be fun. GPT-2, 2 and a 2.4 speed up on long range area. Okay. Because it's like the longer the thing, we have bigger speed ups. I guess that makes sense because regular attention would get slower and slower as the length of the text got larger and larger. Okay. Saying we did better perplexity, which is just a metric on how good these models are. First transformers are better than chance performance on path X. I don't know what that is. I don't know what that is either. Okay. So I think we have an understanding about what they did. At least my main understanding is they did like the tiling, not blocking, tiling, and they did block sparse attention. I don't know what block sparse attention is, but this is my current understanding. They did those two methods, and they got flash attention. And flash attention, is faster and better, which, okay. I mean, I feel like you wouldn't publish the paper if it wasn't better. I would love to have more papers published that were just like, we tried this. It failed miserably. Here's what we learned. Because I feel like everything's like, we created this thing and it's state of the art and it's the best thing ever and nobody could even come close to how amazing we did. And, which I understand why it happens. It's just, then I need to actually read through the paper, understand it, make sure you're not over-exaggerating some parts and you're actually doing things correctly versus if we had more like, oh hey, I did this. I spent a year, I spent a year working on this, and it sucks. Or I spent 6 months or a year, whatever it is, and it turned out terribly. Like, that's a tough, tough paper to write, but I think it would help the community. Because then, if you're like, this is, I guess, two options. One, you don't write the paper at all, and someone else is going to try this, and someone else is going to try it, and a bunch of people are going to waste time. Or two, you do write the paper, but you you massage it so it looks nice. So it's like, oh, small speed up. In both of these examples, then people are going to have to read through the paper and realize, oh, hey, it's actually not so helpful. And you wasted more people's, it's just a waste of time when people either over-exaggerate the papers or don't publish failures. But it's also embarrassing to be like, hey, look at everyone, I made a big mistake. Or, I don't think it's so bad. It's like, hey, I tried this out. It didn't work. Here's what I learned. I feel like it's not. That's what we need in, what is it? Whatever that paper review platform is, we need that. I want, failures. Things we tried and didn't work. Come on. I feel like we're being stupid with this. I think we're going to come back to block sparse attention. We'll come back to this one. Okay. Transformer models. Why am I going to... You know what? Let's... What is it? Block sparse attention. Let's just finish understanding the abstract completely. Sparse attention? Is that what it's called? Block. Oh. What is block? It's not this. Block sparse attention. We probably should also know what regular sparse attention is before we do block sparse attention, but let's start reading and see what it is. Okay. Okay. Standard attention, every token attends to every token. Okay, yeah, full attention. Block sparse attention, only some blocks are active, the rest are zeros. Active computer spaces are zero attention. For me, just so usually we have I have, let me make the spacing a little bigger here. I do not have a cat. I want a turtle. Why do I want a turtle? I don't really know. I wanted one since I was a kid. I feel like they're just cool. I always had a dream of riding around on a turtle, like a big tortoise, and you have like a carrot in front of it. And as an adult, I feel like that would be harder. But as a kid, I feel like it was a cool dream. So usually, so we're doing next word prediction, and we have the word I, and we're trying to predict. Usually it's not, I don't have these values, it's usually whatever, but whatever, theoretically. Trying to predict the next word, or let's say we're trying to translate the sentence, okay, whatever. So every term has a different attention score. This probably should be high. And how much to look at each other word. And then you get scores for these. It sounds like what they're doing is they're setting, it's either you have an attention score or you have 0. So maybe this would just go to 0 and you just wouldn't even look at the word cat. Which sounds helpful and nice, but I guess how do you know what to make 0 and what to make actually have the attention scores for? Like computer complexity drops, memory drops, okay. Why blocks instead of random sparsity? Coolsies. Low compute, fine. Common block sparse pattern. But how do you... Okay, I feel like none of this is really answering my question. How do I know? Sometimes I like to give it the LLM a challenge and just see, like, do you actually understand what I'm trying to say here? I guess this is pretty vague and open-ended. How do you decide which blocks to compute and which set to 0? Okay, local. Okay, so you go 1 by 1. Okay, so I guess there's, you just take the things that are close to you, everything else is 0. Hey, coolsies, I guess, yeah, that would work. Some tokens attend to everyone, and everyone attends to them. So some words, but then how do you determine which words are the universal words and which words are only meant to, only sparse, I guess? How do you choose to pick indices that... Stride block. So just a pattern-based block sparse causal masking. Okay, this is pretty interesting though. I feel like there's so many different in every single thing there's a bunch of sub domains and sub research, and it's pretty cool. Okay, but the idea of, well, we'll understand the idea and we'll go through the paper and we'll understand it a little more. It's basically setting some of the attention mechanisms to, some of the attention to 0 and some of them to higher and lower and so on. Fine. So that's our current understanding, of at least high level, of block sparse attention. I guess. Okay. So let's get into the paper a little. I think we understand the abstract of what they did, sort of. So there's 2 main improvements. First improvement was tiling. Second improvement was block sparse attention. I think we sort of understand both of those, but I think we'll get a better understanding the more and more we read of the paper. Let's see. Okay. I don't know what these things on the bottom were, but whatever. Different we did amazing terms. Let me try to reload this just to, I really like highlighting things. Nope. No. Maybe if I save it. Save. Oh, file. No. A equals these. I guess not. Let's see. I mean, we could do. I feel like a lot of people recommend reading a paper as like read the abstract, read all the images, read the conclusion, and then go through all of it, or different methods of reading papers. Usually, like I mean, I feel like everyone looks at the images, trying to understand them. But yeah, let's just try to understand this, and then might call it a day. And read this more later, but okay. Let's see. Left, flash attention. Tiling to prevent materialization. Yeah, okay, we went over this. We're talking about the middle now? The outer. Okay, let's just try and look at this and see if we understand it. Okay, so this is within the loop itself, so we have this and this, so each one of these is a tile, I'd imagine. So take a copy of it, you take a copy of it, you do the dot product. Oh. Okay, this is pretty interesting. That if you're huh? Okay, so you take the dot product of these, which this arrow is compute block on SRAM. 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 So I guess you compute these, but then I don't understand why this goes into here. If it's because I need a. Okay. My issue I'm having right now is you have the copy here of K and you have a copy here of Q. You compute the dot product, and then you can't really do the dot product with V yet because V is after the softmax. Unless I'm mistaken by that, where you could do QKV and then softmax all of that, but that doesn't. I don't think that makes sense. To me, that doesn't make sense. This is just a copy. Do we have? I mean, this and this dot product. Oh. This is just copies of all these. Like, what are these? Okay, let me read what these pink purple arrows are. Each block flash attention loops over blocks Q matrix, blue arrow. Okay, not what I. Okay, red arrow. That's the outer loop. Let's see. Spatial attention on GPT. Okay, what's on the right? Speed up over pi torch implementation of attention on GPT-2 flash attention. Yeah, we know they don't need to write the large thing. Okay, this is just more the tiling, I guess. If we take a piece, we take a piece. And we output sweat it. Let's try something. Explain. I wonder how well it's going to do. Flash attention. Okay. Yes, we're not storing the full n-by-n matrix. We're just doing pieces. Okay, load all. Compute this. A normal attention. It's like, wait, this is. Fine. Flash attention breaks screen into small blocks of tiles. Sure. Loads only in small part to Esra. Fine. Compute partial attention for the tile. Okay. Update softmax statistics online. Okay, let's break down the diagram. Outer loop, red arrows. Take a block of K, copy it into RAM, use it to compute the block of Okay, I'm gonna go on a sidetrack for a little on, I guess, the other reason I made this talk. I guess the second half, flash attention and life with AI. Sounds like such a click on me thing, but whatever. We'll go over this a little more later. I need a small break of trying to figure this out. I mean, I guess I understand it to like what they're doing on a high level. I guess just going through the details. Maybe I might just try and, I guess, solve this right now. Probably shouldn't include algorithm steps because that makes this a little too easy. Or I can make this a medium question instead. But let's... Okay. I wanted to talk about... What is this? I guess I was thinking life with AI. So I guess it's a weird concept of if we have these magical machines that could do anything we want, and all it takes is we just ask, hey, can I have A, B, C, you know, and I get it. Will I be happy? Like, what's the point of building AI? I mean, I think some of the point is just like, hey, it's cool, and we want to build cool stuff, and I enjoy that. And I do think, I guess, life enjoyment would be. I feel like we'd be more happy. Yeah, we'd have more time. I guess we'd have more time to work on things we wanted to work on. But I guess everyone's born, in my mind, this is how things work. Everyone's born and you live your life and you sort of develop a baseline of your expectations, I guess. And sometimes, life goes beyond the expectations. Maybe make it smaller. Sometimes it goes beyond, then you're happy, and lower, and you're sad, and, on. I do think, I guess over time, I'd imagine the base Okay, this is one person's baseline, so I'm born with baseline, and I do think there's some, deviation in your baseline. Like, I don't think it's always the same thing. I think sometimes, it shifts around. Shifts around. This makes it look like it shifts more down than up, but I was just bad at drawing. And I guess with the addition of new technology, like I wonder if our parents' generation, like, they weren't born with phones, so, or they weren't born with phones, internet, things like that. At least, I'm assuming some of our parents. So their expectations of things and the speed in which they get things, let's say their baseline was a little lower. Because in my mind, over time, let's say, all of humanity, the baseline, our baselines get better and better, Back in the day, you had bread and you didn't starve to death. That's like, that was your baseline. Or maybe it was even lower than that, not getting killed, sorry. And that was the baseline. And then, we advance, and the baseline keeps going up and up and up. And you basically born with more expectations, but maybe, like our parents' generations probably have a different, like their baseline's probably still lower than ours. I think people's shifts, but it stays relatively similar versus our baseline is probably higher than our parents. And our kids will have even higher baseline. And what I mean by that is, like right now, like our expectations are a lot higher than they were, 100 years ago, 1,000 years ago. Like we expect, oh, I need a phone, I need this thing, I need that thing. I expect things to be done a lot quicker. Like our expectations go up over time, which is not necessarily a bad thing. It's just sort of advancement. Now I also wonder, does the curve look like this? Or does the curve look like, or does the curve look like this? Delete this. Why it might look like this is because, I guess for the longest time, like if you went back 1,000 years ago or 900 years ago, the baseline was probably pretty similar in those people. Like there probably wasn't big changes, but now I feel like our parents didn't have cell phones and stuff like that, and things used to take a lot longer. But now with our generation, that's just like 50 years, let's say. Uh, we have ChatGPT, we have certain baselines of, I don't know if baseline is a good word, but I don't really know what we're trying, like what is this, happiness? I wouldn't call it happiness, like I don't know if we're any happier, which is what I'm going to get to. I don't know if we're any happier than people were. I guess it's just expectations of life, like we expect, not to starve to death versus maybe 500 years ago, starving to death might have been more common and obviously not ideal. No one's expecting it, but it was a more common thing. But our expectations go up and up and up and up. And I'd probably say it probably does something like this. Will it flatten out at some point? I don't know, but I'd say currently our expectations are, exponential. And we'll, it's this. So maybe during the Black Plague, it was, during the Black Plague, maybe expectations were living till tomorrow, but and then next year expectations go up. Also, I do think people's expectations shift pretty quickly. Like, I feel like in the beginning of ChatGPT, people weren't so used to it, but we sort of evolved very quickly into like, oh yeah, this is my new baseline. But it still shifts a lot. Like I'm saying, it's still set somewhere. So my thought is, like, I don't. Someone correct me if they think I'm wrong or something, but I don't think people are so much happier today than they were 100 years ago, even though we have all this advancement and we have a bunch of things. And because I think people they always want more. You know, if I have all of this, I want the next thing. Like, I don't think having stuff necessarily makes people happy. And I don't think having I mean, I don't know. I guess if AI takes off completely and, you know, does all the menial tasks and I could just do fun things. Well, like, not fun. I could do what I want, but then the question is going to be, let's say what I want to do is to build something. Well, I mean, I still might build it, but I'll never feel like I need to build something. I'll always feel like something's, I mean, I notice I keep on saying I mean, because I keep on having different thoughts. Uh, People would keep on, I guess we could look towards chess. I think chess is the best example of this. Like, people could feel like, what's the point of learning chess or playing chess? Because everything I do is sort of pointless because there's a robot out there that could beat me. And that might be the future of all humanity. Like, people have that mindset, but still people are playing professional chess, and it's still fun. People still enjoy playing chess, even though there's something better than you out there. So, um, but I don't think it'll make everyone happy, because I guess you could look towards celebrities or this or that, or people that have everything they could ever dream of. And it's still, I think it's the humanity's way of improving, though. I don't think it's a bug. I don't think it's a flaw. I think it's a feature because that's how we keep getting better as people and humanity in general. Uh, the more we learn, I guess, yeah, like the more we have, the more we want. So if we have AIs doing everything, we could think of, you know, build this house, build this thing, and we all live in amazing mansions. We'd probably still We'd probably still not be. I mean, some people will be happy. Happiness isn't, I think, something that will be reached. Like, oh, we are all happy, we're all content. I could work on everything I want and have no issues. But then the question becomes, well, what's the point of building AI? Uh, I mean, I guess it's for the because short term, your baseline isn't gonna move. Like, I guess this is zoomed in someone's baseline. Short term, it's not gonna move as much. It's move a little here or there, but not so much. Not in the spans of times. So if I built AI, maybe, and it could build me a beautiful house and a beautiful mansion, and I could think of a time before that, you know, it's gonna give me some enjoyment. It's gonna, it's gonna make things better for me. I think my kids though, or my kids' kids, they're gonna sort of have the expectations of, oh yeah, everyone lives in a beautiful house and has robots doing all the things, and that's the expectation. Versus me, I'm not used to those things, so my expectation is lower. So, but that expectation, so I guess we build things for our generation. The next generation comes and they'll build things for their generation because the baseline got raised and they're used to that raised baseline, so they want things better. And I guess that's sort of my take on it. It's people, like, I guess this generation, we're building for us, I guess, and that will raise the baseline, and then people will build the next generation, and they'll continue this process. Uh, I guess that's my understanding on how humanity keeps growing and getting better. I don't know if anyone asked for my opinions about this, but I wanted to talk about it and sort of flesh it out myself. Uh, yeah. So I guess the only reason people are advancing things is the idea that things will, like, it'll be great for us. I guess eventually it will be taken advantage of. It, like, oh yeah, this is just life. But for us, you know, this lifetime, next lifetime, I mean, this lifetime, our kids' lifetime, it's going to, okay, you know, it's a nice addition. Like phones and stuff. For people without phones, probably like, okay, this is a cool thing that, and I could appreciate it more than people that were born on phones. Uh, I guess the question is the cycle going to stop ever? I don't think people are ever going to be content. But if AI is able to do things better than all of us, then I don't know, leaves us in an interesting place. Because if we could do everything better than us, what are we doing every day? What are we... I don't know. I think people that have everything aren't necessarily happy. It doesn't mean they're sad. It just means, you know, happiness isn't so simple as getting everything you want. Um, yeah, thank you for dealing with my random aside. Um, let's try and just read through this question. I don't think we can solve it right now, but we'll read through it quickly. Movement road pass of flash attention v1, a memory efficient attention algorithms. Standard attention requires yes. Full attention. Flash attention is OFN complexity algorithm in blocks using online softmax. Number the algorithm. Query key value matrices in tiles. Maintaining running statistics for numerical stability. Okay, so we get an input, we have Q, we have K, we have V. We have a block size of 1. So that's 1 in each direction. And we were given an output of this. So we know what, okay. So we did the algorithm process the attention block. Size 1 to process. Okay. One thing, it's soon we're gonna work on making this better. The notebook feature. This way it'll have some starter code, maybe have a test case. Because right now, like what I want is one of these and one of the test cases so I can play around with it. The starter code, and I want, let's take the first test case. Okay. So we have QKV, which is a 4x4 matrix. Flash attention takes in these and block size 2. And I guess the test is testing if output taken out, 0 element is the same as the correct 0 element. Let's say I just use regular attention. Let's say, did I get this right? QK softmax. Yeah, yes. Softmax takes in X. Let's say p dot exponential x divided by sum of exponentials. It's softmax, and we are looking to get softmax of Q dotted with K transpose. I think all of this is supposed to be divided by I guess in our case it's just gonna be 4. That's square root of 4, so 2. It's the softmax of that. dotted with V. Pretty sure this is just regular softmax if I'm not mistaken. Let me copy this. Let's think about it a little. Why is this taking so long? How many test cases did I make for this? Yeah, this really shouldn't be taking this long. Oh, hey, I got test case 3 correct. Just check the output shape, fine. Did I just compute attention wrong? Why is it negative? Generate a hint, let's see. Implementation is missing a core flash attention mechanism. You're using standard attention instead of block-based approach. Memory flash attention. Yeah, but the dimension was 4 in this case. Fine. Apply that. Yeah, but this should be correct attention, I guess, right? I wonder, is it the same? I guess oh. Asking me why is it negative, and I was like, I guess because the encodings aren't usually negative, but we just took random values, so the, sorry, so the encodings actually could be negative. Okay, it's nice to know I can't just write regular attention and get it correct. Just make, I have softmax of, did I do this right? Very impressed that I got this right. Should I be impressed? Probably not, but I am. What's this? Oh. Yeah, I think the best way to learn this would just be to solve this question. Okay, I'll make a different stream of this, but I enjoy streaming. I gotta go now, but this was fun. Thank you guys for joining. Hopefully I'll see you guys next time. I'll try to do these a little more frequent. I know I don't do it so many times, but I need a haircut.